Professor Jha's lab, right? And you can see all of them working so hard, right? For a course which he is not teaching, for the batch whom they have never interacted, right? But that's a first. So they are going to demonstrate to you something that we promised last week, right? So last week we threw this concept towards you that the interference is actually a single photon interference. Right? It's not that two waves mix and they give you. In quantum mechanics, the probability amplitude, two or more choices for the probability amplitude to converge to a probability. You will always see the interference effect, be it a particle, be it a wave. Doesn't matter how you understand. So that's what we are trying to, we'll try to demonstrate today. Right? We will use the same laser source, attenuate down to an extent such that, it really, literally becomes throwing bullets out of a gun or throwing ping pong balls out of a sink or court, something. So just the photon picture, and then we'll demonstrate that yes, you still see the interference pattern building. So that's what is the goal today, and I hope you guys will understand it, appreciate it, and enjoy it.
Okay, so in the last demo, I think we addressed this idea that interference from quantum perspective is basically interference happens or takes place when you have the indistinguishability of the photon paths. That means if you cannot figure out if it comes, yes, okay. So when you cannot figure out which way the photon actually goes and hits the detector, then for example in this case, you could identify the photon based on its polarization, and so there is no interference, but then we saw we can just erase that possibility by putting a polarizer at 45 degree here. So that now if you take a photon here, that means if you take a photon here, it is 45 degree polarized, so you have no idea whether it came this way or that way, because V will also give you a 45, H will also give you a 45, and then the result. So last, and then we said this essentially means that each photon interferes only with itself, and that interference between different photons. Next slide is written as well. Okay, so the thing is that we then kind of concluded the only way you could explain these ones, this kind of experiment, is that by saying that in photon, I don't know what is interfering with what now, but something is interfering, this is not quantum interference.
Better from here. Changing slide from here.
It's better? Okay. I don't think so.
I think this slide is not. You don't like this slide. But this may not be connected to.
So that's the way. We can go back. Right. Okay, so we'll start again. Hopefully it works this time. So, alright, so today we are going to do, next slide. Today we are going to, next. So we'll demonstrate this aspect that interference means each photon interfering with itself. This we will demonstrate with this Young's double slit experiment. So again, right now you just see one slit. So it's a light source. This light source, well, if it goes through, this is a opaque screen with a slit cut into it. So if light goes through it, of course, there's a uniform kind of pattern that falls onto the screen. And then it will definitely have a size. So if you go towards the corner, then the intensity kind of drops down. If then we put another slit, if I had just one slit, again it will be the same pattern, but if I put both, then you have this interference kind of pattern that I think everybody is familiar with. That if you put a light source, two slits, you get interference pattern. Now, the question is, well, maybe one more. Fine. Now, how do you explain this? This again we did last time. So within the classical wave theory, we explain interference in terms of division of amplitude. That you have a field coming in, and you divide that field and some amplitude goes through this, some amplitude goes through the other slit, and then you add this amplitude, superpose them, and that's how you actually see the interference. But one consequence here is that when you divide the amplitude, you're also dividing the energy in the classical wave description. That means if you had, let's say, 1 watt of energy falling onto the screen, that means, like 5 watt is from this, 0.5 watt from that. So division of amplitude is equal to division of energy, and how we explain interference is through the superposition of amplitude. So this is how we explain the interference within the classical wave theory, and it works. Everybody knows that it actually works. But now the question is, this light source, or maybe you can, yeah, that's fine. Go. This light source, now what I want to do, well, this is giving me interference pattern. What we want to do now is reduce the intensity of this light source. Okay? So I have a knob, well, not a picture, but let's say I have a knob. I'm reducing the intensity of this light source. So this is when it's brightest. Now if I reduce the intensity of light source, what will happen to, if I look at the screen, what will happen? Any guess? Huh? Intensity of the pattern will go down, but you will see the same pattern for sure. And same contrast as well, that is maximum, there's a maximum, the minimum is 0 and so on. Okay, so yes. So if you do that, the intensity actually goes down, but I don't know if you can see it, there is a pattern. This is the maximum, this is the minimum, and so on. What if I reduce the intensity even further? Huh?
You still get the pattern.
You still get the pattern, but any change?
But the intensity will
Overall intensity will kind of reduce. Okay, so let's see what happens. Yes. So you still get the pattern. Overall intensity has reduced so much that maybe I can see, you can't see it, but yeah, the pattern is there. What if I reduce the intensity even further? Huh?
will still be there. But
Visibility will be gone.
Visibility will be gone, but the overall intensity pattern should remain the same. So if I come in with a stronger, better, nicer, more efficient camera, I should be able to then see the pattern, right? Let's do that. Oops. So that is not what happens. So if you keep on reducing the intensity, there comes a point where you actually do not see the pattern. What you see, you can still see the pattern. There's a vertical thing here, vertical thing. There's a sense of fringe pattern, but this is not a fringe pattern, this fringe pattern. And of course, now you see this brighter yellow dot because now I have brought in, theoretically, a much nicer and stronger camera. And of course, this is rescale. So each dot represents one photon. So there's no concept of intensity now. Each photon is representing, each dot is representing one photon. So what is happening here is that if I just keep reducing the intensity, then there comes a point where you will stop seeing the fringe pattern. You will then start seeing just the dot pattern. Okay. So what if I reduce the intensity even further? Huh?
less.
Number of dots will actually reduce. Okay. So yeah. So that is a correct guess. Number of the dots, that means the number of photon that is actually has reduced. So this is exactly how it happens. The light high level intensity, you see the fringe pattern. If you just reduce the intensity, the pattern is there, but overall the intensity becomes smaller and smaller. But then there comes a time where you'll start seeing the scatter plot. At this level there is a sense of fringe pattern, but at this level there is really no sense of fringe pattern. You have 5 or 6 dots and you cannot make out where is maximum, where is minimum. But it's still here, by looking at the density of the points, that means density of number of photons, you can actually say, that yes, this is maximum and that's where the minimum is, or that's where the minimums are. So this is with the Young's interference. But let's say if we repeat the exact same thing, but no complication of this interference thing, just we'll have just one slit and we'll repeat this entire procedure. So with just one slit, again I have kind of like uniform intensity in some region and then kind of decays down. So now if I reduce the intensity, what happens on the screen? Visibility will decrease, well the pattern remains the same. If I decrease the intensity even further, same thing, fine. Now what happens if I decrease the intensity even further? That's the fourth step. So yes. So So again you have this, so there's no interference. So there's no interference, but this is overall intensity. Again you see the sense that yeah, there's more dots in the center, towards the sides, maybe not as many. But so you get a sense of whatever the intensity was, now you are getting that in terms of the intensity of the dots or the number of photons per unit area. But as you reduce the intensity, you get to a point where you no longer have this continuous intensity pattern. What you have is just this dot pattern. What if I reduce the intensity even further? Yes. So what is happening here? So up until this one is fine, this onwards is also okay. But this, between these two, what is happening? Whether I do it with just one slit or two slits. What exactly is happening here?
It shows the same particle behavior.
Huh?
It shows the same particle behavior.
It shows the
Particle when it comes to the scattered particles, it shows the same behavior. But as a wave, it shows interference in double slit and
right. So first of all, classical wave theory you can explain up to this point. It's perfectly fine. But you can no longer explain from this point on because the division of amplitude doesn't work. So what do you do in quantum mechanics? You do division of wave function. Now division of wave function doesn't mean division of energy. That is the main point here. That if I have a photon going through two slits, it's not the half the photon goes this way, half the photon goes that way. Just like the electric field amplitude, half of it goes this way, half of it goes that way. But when it's a photon, and if I have two slits, it is not that half of it goes this way, half of it goes that way. It either goes through this or through that. And that's why you see a full dot. This dot means one photon. You never get a half a dot. So you can't explain using classical, from this point on. So how do you explain it? It's using quantum mechanics. That is a superposition of wave function, which does not necessarily mean division of energy. And what is happening here, actually, at this plane, actually, because if light field or if even a photon field actually goes through a slit, so whether it's a light field or a single photon field, it has a possibility of being found anywhere on the screen, right? That's the light field I have. So since I have this possibility of finding anywhere, why am I finding it at just one place? So this single photon, if I let's say have a single photon source, which we do, and hopefully we should be able to kind of show it to you, that if I reduce the intensity to an extent that I'm just sending one photon at a time. So now of course I'll get and in these we will construct actually that again, if it works we'll show it to you, that on the screen we will get one photon at a time and then kind of itself. So what is, as far as detection is concerned, what is happening at this level, at this plane?
You are measuring it, so even if there is a possibility of finding everywhere, if you are measuring it, you are collapsing it.
That is the collapse of the wave function, right? That if you have a state and when you measure it collapses into one of the eigenkets of the measurement operator. So in this case, if I'm measuring the position, so the entire wave function collapses at one point, one spatial location. So even a single photon has the possibility of being found anywhere, but when you actually do measure it, the entire thing, the entire energy is found at one point. Okay, so this is a very strange aspect, but that is the aspect which you refer to as wave-particle duality. That photon is a wave as well as a particle, and simultaneously. It is not that today it's wave, tomorrow it's a particle. It is wave and particle at the same time. And the wave function collapse, I mean, it's not a physical concept, it's just a concept that says, you say that I don't know is replaced by wave function, the collapse of the wave function. Because there is really no time scale associated with this. You have the wave function, you make a measurement, and it immediately collapses. There's no time scale associated with this. So that is how it happens. Right. So maybe one more. Yeah. No, back. So what I tried kind of convincing you through that level. Well, this you already know. I'm just putting it in a perspective of what I'm actually going to show. Just one simple idea of wave-particle duality. So how do I look at light, or what is light? It is wave and particle at the same time. You can't see. If you come so close, you can probably see the tiny dots on that here. But the point is, the light is a wave as well as a particle, and this we see in Young's kind of fringes when you see the fringes, but you also see the dots on the screen. So it is wave as well as particle. So if you think of wave, how do you think about it? What is a wave?
There is some quantity associated with the wave that oscillates in time.
It's some sort of disturbance that propagates.
It propagates, and so it's something spread over, right? It's a wave, and when you say particle, what do you think of? Something localized, right? Particle means something localized somewhere. Wave means completely spread over.
Then what is the standing wave?
It's also a wave.
But it does not propagate.
Well, standing or doesn't stand somewhere. It is, between that wall to that wall. So again, you don't say standing wave at a point. Well, the amplitude of the standing wave at a point, that you can talk about. But when you say standing wave, you do mention some region. So I mean, spreading over doesn't mean it has to always spread over infinity. But it is not localized like a particle. It is localized somewhere. But the moment you say wave, you think of water wave. You think of tube light, wave coming out of the tube light. Again, this is all over. So wave means something that is spread over. Particle means something that is localized. That's one point. Now, what we see in the description, right, or for that matter, any quantum system, that quantum system is particle and wave at the same time. That is wave particle duality. And this essentially means that the system is somewhere and everywhere at the same time. Right? System is somewhere, that's a particle, and everywhere, that's a wave. But this is happening at the same time. Does it make sense? No. But is it true? Yes. So if you go next. Right, so this is kind of like the summary. So in classical we said division of amplitude, that's how we'll explain superposition. That actually means division of energy, and then superposition of amplitude gives me interference. One more. And one more, yeah. So this theory is actually fundamentally incorrect, classical theory, but it actually works at the highlight level. So for highlight level, you don't need to worry, you can keep doing the same thing. But this theory becomes inadequate at single photon level. The moment we start seeing dots on the screen, classical cannot explain it. But in the quantum theory, the main difference is the division of wave function. Here we don't do division of amplitude, we do division of wave function, which does not mean division of energy. So this is fundamentally correct at every level. On the 6 screen or 5 screen that I showed, it works at every level. So it is fundamentally correct and it works at every level, but you necessarily need explanation only at single photon level. Because quantum is mathematically little involved. So if you know that your experiment involves only highlight effect, you need not use quantum theory. But it works at highlight level as well. It is not that quantum theory works only at low light level. But you might need it only at the single photon level. That means when the light level is very low. Okay, so this wave particle duality that we see in the context of even without interference, you have what do we have, that the system is somewhere as well as everywhere. And if you bring in the interference, then the interpretation that comes is each photon interferes with itself, because since it's a particle wave at the same time, if it goes through 2 slits, it either goes through that or through that. And the entire thing then you see on the screen as one photon. So then how do you explain? You explain this using each photon interferes only with itself. Interference between 2 different photons can never occur. Does this statement make sense? No. Is it true? Yes. But so this is the best description, even though it seems nonsensical, but this is the best description that we have so far. So, yeah.
If you go by this statement, why do we need coherence?
No. So, when you bring in coherence, it's like, okay, this says each photon interferes. So, when you have full coherence, then only it will interfere. But if you have slightly lesser coherence, it will also interfere, but not with that high contrast. So, coherence decides how it is going to interfere. You can quantitatively kind of quantify as how much of interference that will happen, what will be the contrast and so on. But why the interference happens at the level of single photon, for that coherence is there in classical as well as quantum. So that need not be. Okay. So coherence is there in classical as well as quantum. It is basically the electromagnetic modes, the way you define it. It remains same classical and quantum. There is no difference, zero difference. But here, when you do get to the single photon level, then how do you explain interference? Coherence explains how much of interference, 100%, 90%, 10%. But this is basically why interference at all. How come they are interfering, or how come it is interfering? Because there's no they, just photon is coming one by one, and then you will see the entire pattern building, which is what we hope to kind of show you. So this is why a photon interferes, and that is the best explanation, even though nonsensical, but that is the best explanation we have so far. So, okay, so just go one more. Yeah, so this is what the plan is, that we will first show you with both a uniform kind of source, and hopefully we should be able to show you the wave function collapse, and then you start seeing dot structure, and then we'll bring in these two slit situation, and then we'll show you the detection of these photons one by one on the screen, hopefully, and that then eventually will build up and will go up to this point. Okay. So, any quick question for now before we switch to experiments?
If we give it enough time, then it will, that last one will tend to the second last
Yes.
one.
Yes. So it will just accumulate. We'll just accumulate. We can increase the rate of accumulation as well. So, but the point is, it is made up of those dots. There is no uniform intensity. It is made up of those dots. Of course, when there are, let's say 100 dots, you can identify, that it is actually dot structure. But when you have few millions, you can't. That becomes continuous. So, but that is a fundamental explanation. That is what we want to kind of stress and kind of fine.
So at the single photon level, when we are not measuring it between the two, like we are measuring it only at the screen, do we still interpret it as it either went through this slit or this slit?
Yes, I don't have this in the picture, but if I make sure that I have a single photon source that it emits one photon at a time. Again, this fact I won't be able to prove. You kind of have to believe me on this. But the point is, that's also the quantum theory, that photon, the minimum energy it can have is h bar omega. Let's talk about half h bar omega right now. And how do you increase by h bar omega? So, and what is this? These are the detectors. They work, the atom goes from ground to excited state and then comes down, and that's how it actually. So you can make sure that you're sending the photons one by one, and then you will see the dots coming on the screen one by one. So, and then there is quantum theory doesn't allow you to kind of divide the energy. That is simply not possible that half h bar omega goes this way, half h bar omega goes this way. So if you have only one photon in the system, then it is like either goes through this or through that. If you have two, then there could be that, okay, one went through this, one went through that, and they had some hidden agreement that, okay, do you land there, I'll land there, and so on. But if you have just one, then you have no idea. Maybe the photon, the stream that is coming, let's say maybe they have a hidden pact. Oh, first one you end up there, second there, third one you go there, and so on. But you find that if you actually decrease the rate of flow of photon, let's say you do one today, one tomorrow, one day after, it will still give you the same pattern. Of course, for that you'll have to wait for some 7 years or something. But the point is still, whether they are separated by 1 second, 1 millisecond, 1 year, 1 light year, if you wait long enough, you will get the same pattern. Theoretically, practically it won't happen. Yes.
So, like if our interpretation is that it either went through this or this and came to the screen, then why would we measuring it whether it went through this or this affect the pattern? Because either way it has gone through either this or this.
Yes.
So why does my measurement of the fact that it went through this or this affect the interference pattern?
Well, that part I haven't talked about because fine. So that part I haven't talked about, but that does happen. So what is the question?
Like if our interpretation is that regardless of our measurement, it either went through this slit or this slit.
Yes.
It's not like it went through both parts and only.
Yes. So why does our measuring? So when you measure from very fundamental perspective, when you measure, you disturb the system, and here is a single photon system. So when you make a measurement, you can't make a measurement without disturbing the system. So that can be kind of answer to that question as to and then there's a complementarity to the extent that you disturb, you lose the interference capability and so on. But it is as simple as the moment you kind of disturb the system in trying to figure out whether it went through this slit or that slit, that changes the wave function in such a way that it gives you what it gives you on the So if you just ever so slightly, you will probably have interference but not perfect contrast. But if you completely disturb it in the sense that now you know for sure, okay, when this way or that way, then you would have kind of destroyed the interference pattern completely.
Sir, even with a single slit, we get to see a diffraction pattern, right?
Yes.
Would we not get the same if we were like using a single photon in the setup like that?
Diffraction pattern? Yeah, yeah. So, yeah, I mean, you probably know too much. So yeah, single slit diffraction pattern, but the diffraction pattern, you know, it's like uniform intensity, and then there's some filters and so on. So yeah, I just kind of wanted to make it like simpler, but yes. So there also is some interference effect, but not as pronounced as this one. So or you can have just a beam of light. For example, this is also beam of light, and in a sense, this is also diffraction. So diffraction is the way light propagates, but it's like a very uniform intensity, and versus when you see clear kind of fringes. So that's why I want to kind of distinguish those two. That wave particle duality, the measurement aspect. You don't. It is not necessarily that these you see this concept only when interference explicitly occurs. These are independent of interference. If you have a wave function and you make a measurement, that's where the wave function collapse happens. The moment you make a measurement, it collapses into one of the eigenvalues. And as far as the wave particle duality is concerned, again, doesn't matter what the interference happens. You have the quantum system behaving as wave and particle. If it behaves only as a wave, then you can explain it using classical waves. So all the results in quantum mechanics, where you are only looking at the wave aspect, you can actually explain through classical waves. All the results in quantum mechanics that are only particle type, particle behavior, you can again explain through Newtonian mechanics. But only when you have both of these together, that's when you cannot use either the classical wave or the classical particle theory to make quantum.
So each of the parts has a different wave function, and the particle's wave function is the superposition of these two. So wouldn't the inference from that be that the particle is going through both at the same time?
Particle is not going through both at the same time.
I mean, photon is going through both.
Yeah, I mean, that's how you can say it, but it goes through. Well, that's not how we say it, because we know it goes through only, that's what you were just saying like a moment ago, it goes through only one state. Now, how do you explain it? You say, it interferes with itself. But you simply cannot have the photon going through the two states, because quantum mechanics does not allow you to kind of divide that h bar omega any further.
Take out the monitor and reconnect it.
So, then it will be like h bar by 2, h bar by 2. Then there should be some way of measuring that h bar by 2 right above the first state. Right? And if you don't look at the second state and you just sit with the detector the first state, then at least once in a while you should see that h bar by 2. But you never see that. If you actually sit there with the detector, you will always see h bar omega. So that has been proven that you don't divide the energy. It remains the same. And then again, when you detect it from the detector, you again detect the entire h bar omega. So it means it went the entire h bar omega through one of the slits, and you detected complete h bar omega. But again, that h bar omega, when it's kind of like spread over the entire area, suddenly if you make a measurement, the entire thing comes onto a pixel of my camera, which is about 16 micron by 16 micron size.
So, sir, we identify the photon not by its wave function, but by its energy, which cannot split.
That is the quantization. That energy is fixed. Wave function you can divide and split as many times as you like. But the energy, that is the main prime quantization idea. That once you fix a electromagnetic mode, then you can only increase its energy or decrease its energy in the steps of h bar omega.
So we identify the photon by its energy, so we don't infer that it goes through both. It goes through one because energy comes.
Photon is h bar omega energy. Yes. That is the concept of photon. Once you have h bar omega energy, that's what you call it. A photon. Whether that h bar omega energy concentrated in this tiny region or over all space, it is still a single photon. Okay. Yes.
Sir, if you put detector in the both the paths.
Are you ready? Experiment?
There is some issue with the
projection. So maybe we can.
So if you put detector in the both the paths, so eventually when we start the experiment, we would randomly find photon going from this path and also from this path, even though we don't see it, right?
If you are sitting with the detector next to the slits,
Only the slits are in the path. just to detect from which part the photon went through.
Okay.
So we would randomly find photon.
Yeah, you randomly find it is either this or that. Yes, the entire experimental.
You cannot see the interference pattern.
There you cannot see the inference pattern. Well, and the reason, that's precisely what he was also asking. The reason would be that the moment you make a measurement, or the entire process of making the measurement disturbs the system. So you are seeing the interference, but you are seeing the interference of that disturbed wave, which is like a uniform pattern. So because that can also be quantified, so the way you make a measurement, that can be mathematically modeled, and then you can show that it disturbs the system in such a way that the new pattern that you see on the screen has no interference or has less contrast.
Here also, if we know from which slit a photon is coming, and here also interference pattern will disappear.
Yes, it will. Fine.
I mean, it's also projecting the SLM to that one. Right? That was the screen. So when you say duplicate, it duplicates everything. So that has to be there.
Oh, yesterday we didn't.
Experiment is working.
Oh, we didn't try the projector.
What try the projector?
This is the fun of doing experiment, especially these experiments. If you are able to do it, that will be some achievement. By the way, we are not showing it to you. I have 40 lakhs worth of equipment here, just so you know. So when you are leaving, you can take a look, but maintain some distance, treat it as having COVID or something. So, but the idea was to kind of show you something, what you kind of study. So
duplicate 2 and 3. So 2 and 3 will be like.
Any other question while? Yes. Yes. So if you put a detector behind the, let's say, one of the two slits, then you know when the photon comes. Again, if it comes through the slit where you have put the detector, it will go click. So that then you know it came this way. And just the fact that you have the path distinguishability information, there will be no interference pattern. That is a very simplistic way of saying it. The other more precise and more complicated, accurate way of saying it is that that act will disturb the wave function, overall wave function, and that wave function will be interference pattern.
No, 2 and 3 are same, no, and 1 is. Yeah, no, it's
Well, everything is disturbing, but if that disturbance, if you want to kind of correlate, if that disturbance reveals, this information as to which path it actually came from, then you lose the interference. That means that disturbance is not as severe to kind of complete disturbance. So this is a very simplistic way of saying that if I know which path information, that's just a very black and white explanation. But disturbing the wave function, that can be kind of quantified, you can actually work out, you can calculate. But overall, if the situation is such that you cannot extract which path information, no interference. If you can extract which path information, there will be.
Okay, Anand.
So opposite. Ready? Okay. So before it starts working, stops working. Now
This quality goes down and
Earlier it was
you cannot see the screen properly.
fine, that's okay.
But individually
you stay here. We'll after I show you this setup, at least from top, then we'll close this. Try to close all these. Since we need to invite single photons, we need to drag away these millions of. So this is the setup we have. So this is the top view. Since there's a laser on, I hope nobody is seeing any reflection or scattering of the laser. If anybody does, just shout. Then we'll put a. This is a very harmless laser, only 5 milliwatts, so it should be fine. But still, if you see any scattering, do let us know. So here, what you have, this is a laser, same laser that we brought last time. There's a mirror over there. This reflects here. You can see this red shine. That is actually laser. If I turn it off, which I won't, because we don't want to take too many chances. There's another mirror over there, and this is probably smart camera. Can we stop its smartness? No, fine. So these are some, that's a mirror, that's a mirror, then we kind of expand the beam, and then again that's a mirror. Well, that's a mirror, and then it comes onto this piece. This is called spatial light modulator. Okay, so with this piece, I can generate any pattern that I want. Here we are interested in generating double slit pattern. So, well, believe it or not, making a double slit pattern and seeing the interference is very hard. Those who have done it, in books you have been reading it since class 3, the double slit, well, little exaggeration, but making double slit is very, very difficult. We spent 3 days, then we realized that I didn't want to bring this device to this is my 10 lakh device, I didn't want to, but then again we could not make very good quality double slit. So I brought this device. This is an electronic device, and with this I can make any pattern, like my face or anybody's face for that matter, and we can actually put it on there. So here what we are putting, we'll put either one slit or double slit one by one, and then from this SLM we'll have this interference pattern, which in this case will be either the single slit diffraction pattern or the two slit interference pattern. And then we have a mirror over there, then this one is a mirror, you can see the spot here, and then this goes into this camera. This is a single photon camera. This has smaller number of pixels than the camera you have in your pockets. You at least have 10 million pixels. This one is 250,000, so 250,000 pixels. But each pixel is single photon sensitive. So each pixel can detect single photon. So I literally have 250,000 single photon cameras in 512 by 512 array. Okay. This camera has been cooled down to minus 60 degrees Celsius. Room temperature is about 20, but this is minus 60 internal, at least the sensor area. And this is capable of kind of detecting the photon one by one. It also works at slightly high light level, not too high light level, slightly high light level, but we can bring it down to single photon level. So the idea is that first I will show you a slightly high light level pattern that we are after, and then we will reduce the intensity of this thing so much, we will do that all electronically, that you start seeing on the screen photons hitting one by one, and that eventually hopefully will build up the pattern that we are interested in. Okay, so we'll start with the single slit. So now what I'm putting on this SLM, something shaking, what I'm putting on this SLM is a single slit.
On the right side, that's a slit.
So essentially what is happening, that's a source, very simplistic. That's a single slit, diffracts like that, and at the screen, and this is my SLM, or you can say slit. Okay, so that is a pattern we are putting on the SLM, and then what gets generated. Okay, so then we'll not show you the high intensity pattern because that kind of kills the fun. That is giving out the answer. So this is the screen. So are we showing one screen at a time or both? Which one are we showing?
This is the first screen, one individual photon.
And then we move on to that one. Fine. So this is the screen which gets the photon one by one. That means like frame by frame. Each frame is like 0.05 second.
Yes.
So each frame is 0.05 second, 50 millisecond. So you keep your detector on for 50 millisecond and see how many photon came in, and the way we have adjusted the experiment, that it should be just 1, 2, 3, that many. So it's like 4 photon coming on to being detected by 250,000 single photon cameras. Okay, so this has to already, and then on this side we will be accumulating all this frame by frame, and after a while we will see a pattern. Okay, so let's turn off the lights.
Anand, don't do that. We have set it according to this ambient light.
Okay, but then I don't see anything here.
Right now there was one.
Can you see some dot?
Yeah, actually, this is
See that you can change, no? That threshold you can change easily. But with the light, this will not be visible.
Means
So-
I'm not able to see anything. Like we are able to see here stuff.
I know, but you need these guys to see. Okay,
Yeah,
fine.
yeah.
Yeah. That is gone. Oh, that I don't think we can do much about it.
And
Can you
that
see something?
window we cannot do.
And focus on this one. If you keep focusing somewhere else, then you won't see it. It's a single photon. Right, it's a single pixel which is lighting on that big
Okay,
screen.
well, can you expand that window?
Yeah, no.
So this is frame by frame. Maybe you see some blip somewhere because this will come and go.
Yeah.
See that? So that acts as a single photon hitting that camera.
Yeah. Now this is yeah.
This is 0.05 second, and then it's the second screen that comes. So it acquires, displays, acquires again. So there's a electronic delay as well. So the thing that you do, that means there was like 2 photons. That was like right there. So if the thing that you're barely able to see, that was actually 1 photon. So you kind of like see that maybe 4, 5, 6 photon per frame that you have. Can you increase now the rate a little bit more? Not too much?
290.
You see more, right? So now at least some
More
20,
frequent.
30 photons for that 250,000 cameras that we have. Okay. So this is frame by frame. Now we can go back to the main accumulated, and this frame, it has just accumulated everything so far. Okay. So now you can see this dot structure. Each one is a single photon. Wherever you see slightly, slightly more intense dot, that is actually 2 or 3. That means the 2 or 3 photon, in different frames, they happen to arrive at the same spot, and that looks slightly bigger and brighter. But it's essentially individual dot is what you're kind of seeing. Okay, maybe you can increase it more. So what are we expecting in this case? More or less an uniform pattern, because this is a single slit. We will not be able to resolve that single slit diffraction pattern. Increase it even further.
Even further. I mean, now you can see it here also. Like, so this is the instantaneous, and that's the average.
Yeah. So per frame,
accumulated
now,
one.
the thing has increased, and then you can see there's a kind of band, like there's a less intensity here, less intensity here, kind of more like uniform intensity here, because the slit was in this direction. And then the source, laser source intensity, that decreases after kind of this one. Of course, you might see some stripe and stuff. That's because of other, stuff, not really the thing. But if you again accumulate it for much longer, it will be complete uniform pattern. Any question? Okay, so maybe then
move
we
to
can
the
second double slit,
slit.
yes. So this was just to show that the single photon aspect is there even when the explicit interference is not there. But now we will show you the interference. That's really highlight level. Now you cannot make out any dot, right? So that's really highlight level. And you see that my camera started crying. So that is saturation. So this is very good, but only at low light level. If you expose it at highlight level, you can easily burn it. Now double slit. Fine. Okay. So now what we have, sir? What we have is a double slit, and those who can do the calculation, what is the size of the slit?
4 into 8 microns.
32. 4 micron.
32.
So the size of the slit is actually 32 micron, and the separation is
480.
Separation is
4 inches per micron.
16 to
480 micron.
480 micron.
Well, this we have the numbers we have chosen after several iterations, so that there is some visibility of what we do. So again, this is a frame by frame, 0.05 second. And again, I haven't told you that I have put a double slit there, right? You don't know what to expect. So if you just look at the screen, the experiment has already started. Maybe you can see something, the dot shining somewhere. Maybe, I don't know if people can see it at the back. This is right now just 2-3 photons.
Yeah.
This is too bright actually.
Yeah.
We should have thought of this one earlier. But yeah,
See
that
these dots
looks
coming,
like
right?
1 or 2. So now if you increase the rate,
Increase the rate more.
no, it's fine.
Rate is okay.
Just keep it here. Right, yeah, we can display this now. So maybe some of you might start seeing, these vertical lines here. So, but again, one thing you should notice: this is made up of dots. There's no continuous anything. It is made up of dots, and as we accumulate, you will get more and more kind of dots there. So maybe you can increase the rate a little bit more. So hopefully now, since there's a frame by frame, difficult to see, now hopefully you can see the dot structure building up. So initially it was not clear what it was, but now you can get some idea as to what you are kind of getting as a pattern. Can you see in the back? Okay. So, the frame by frame was difficult, but here you can see, and each dot that you have is a single photon. If the dot is brighter, then that is each dot that you have. If the dot is brighter, for example, that could be 2 or 3 or many photon as well, because this is now increasing the photon flux even further. So I don't know the numbers, but maybe now you have about 100 or so photon per frame. That means 0.05
Can
second.
you show that other frame?
So again,
instantaneous one.
now so this is how many photons, about 100, 200 per frame that we have.
So if you take a snapshot of this, you will never see the interference pattern, right?
Yeah,
Because
so
it's not that the energy, as I said, its energy is not getting distributed. So you only see like some bunch here or the line or some line there or something like that. But over the time, when you keep accumulating it, then you just see that, okay, fine, the photons are distributed along that pattern, and that's a single photon interference.
So there was this theory called pilot wave theory. People said that maybe the photons that are coming, they have had a confidence earlier, and then they decided you go there, I go there, and that's how they produce interference pattern. And it actually works. You can actually do that. But it turns out for a slightly higher order quantum effect, that pilot wave theory actually doesn't work. So far, quantum mechanics has no competitors. It doesn't make sense, but it is the most correct theory and accurate theory so far. So now you can see, since we have accumulated photons, you can see some continuous kind of pattern as well, but still more or less it is the dot structure that you are seeing. Any question? We can run it for a while you enjoy.
We have another 5 minutes.
Yeah. So I think it is 5 minutes. We can't do much.
Highlight level, we can show them.
No, I don't want to go to my laptop now because
That's a video recording. So I'll tell you, this class, I'm also lucky in that sense, and you guys are one of a handful people, and that handful will be like about, I don't know, a lakh people, a lakh or, couple of lakhs. But we are those people who have actually seen a single photon camera, seen the interference pattern develop as it explained in the textbooks. We all learn it, we all accept it, right? You all will be able to calculate all this, and you will never see this, right? I did not see this before yesterday. I knew everything, right? Of course, and it's easy for you to get convinced by that argument, right? That I knew everything because I'm coming here and teaching you. And yet, I know all the theory behind single photon detection and all that. I had never seen a single photon camera. I had never seen what it really is to make that experiment and what to expect from that experiment, right? So now once you have seen it, you can never go back and say, there is something else which we are missing. It can still be explained classically and all that. Now you just cannot explain that. You have seen it in action. Right? It's not that information is not told to you. There is just information to tell. This is how entities are going to behave at a fundamental level. Okay. Have we lost?
No,
we are coming back.
So, now we'll stop the experiment, and I want to show you some fun stuff. That this is, we can't show you everything live, but what you saw is the single photon giving you an interference pattern kind of building up. So now that you're convinced that each dot is single photon, now we'll make the photon dance a little bit, and so that will be a little kind of exciting. Can you see it?
Yes.
Okay. So this is you keep that laptop somewhere. Okay. So now, so here you will see also the individual dots over there. So those are. Where is my laser pointer?
It's okay. Nice thing.
Oh, this guy just wants to dance, but we'll so what I want to kind of emphasize. You see, this is red because this is done with the laser. This is not actually single photon. Well, this is about 10,000 photon that you're seeing here. It's a, like scattered dotted structure here. This we have recorded, and this is not happening live. So this is 10,000 structure, and this is the SLM, the device that I showed you. Here we are putting the Fourier transform of this person, and so that when we actually have it in the camera, this is the structure that we see. So it is not a single slit, double slit. No, it is a very, very complicated pattern that we are putting in, and this is what we see. And then what we do in that SLM, we just change these the aperture 60 times a second or 10 times a second, obviously. And then, yeah, 1, 2, 3, go. Okay, so this was 10,000 photons dancing. One last thing. This is only to convey the quantum mechanics is fun. Yes. So this is not at necessarily single photon level. This is a highlight level. Again, this SLM, this is we are doing a highlight level. This is no regular camera, but this is just one last fun stuff. Have you heard of Gangnam style? So towards the end, a little bit of Gangnam style is also there. Okay, so 1, 2, 3, go. Can you remove that arrow so that, fine. Okay. So this is the aperture I'm putting on the SLM. It's a very complicated aperture. So double slit, single slit is an aperture, this is also an aperture. It's just changing 60 times a second. That is enough time. All right, thank you so much. Okay, so maybe if you have a quick question, this is 10:16, so I think we have some 5-7 minutes. So if you have a question, we are around. If anybody wants to just take a look, I think do it from a distance because this is too expensive. Question? Yes.
That dancing video, like you took one frame and one aperture and then compiled it.
Yes. No, this is actually real. I can do it in my lab. Project it on the screen and then the record it.
Aperture will change according to how you program it.
Aperture will change according to how you program it. The first period is changing like 10 times, the last period is changing like 6 times. That is the maximum time. Okay. Okay, if no question, I think we are done. Okay.
Class is done. And we'll revert back to the boring stuff from the next class.
Thank you so much. Well, again, these are my PhD students. This is Pranay, Radhika, Suman. I think they have done the hard work.